Um, 1, 2, 3. Do you hear me? Hi all.
Hello.
Do you hear me? Good. Shall we start? Now, let me first tell you my plan for the next 2 weeks. First, on the 9th of April, you most probably will have a class test. You'll be sitting in a class, and I'll be sending you, or somebody will print out some questions, and your task will be to answer these questions. Details later. Now, so before that, we are going to have 2 lectures or seminars or whatever, however you want to call this, our activities. Now, and I have 2 areas, 2 technologies to cover. Now, I'm not going to go into all the details. Instead, I'll concentrate on the practical aspects that will be relevant to your test. Today, I'll show you how you can use the language which is called R2RML. Yeah, this is a W3C standard language for translating relational data, relational databases into RDF datasets. Relational data with possibly very complex tables, schemas, how to translate into kind of humanly understandable RDF sets. That's one thing. And another one, I'll show you a few examples of how to write ontologies, more complex ontologies in more complex language, in fact, in the language OWL2. Now, for this, I'm going to use concrete examples, and I'll show you how to design, or we'll be discussing, hopefully, how to design an ontology using the Protégé ontology editor, if it works on my computer. And I'll show you at the same time how you can write the same information and how you can represent the same ontologies in a kind of mathematical language of description logics. And so I'm going to do this using examples. That's the plan for today. Next time, I'll prepare some exercises, and I'll show you how to answer those questions in these exercises. And they'll be kind of similar to the questions in the test. So that will be your training. So today, some new stuff. Next time, just exercises, questions and answers. Okay, so let's go then. As we saw last time, to translate relational data into RDF, you can use, for example, the system on top, or there are other free available systems where you do the following. So let me first remind you of the setting. Suppose we have a relational database. For example, we have a couple of tables in our database. The tables are about movies, and in fact, it's a little bit simplified version of the IMDb, of the real IMDb database. Yeah, I gave a reference. No, okay, I gave a reference somewhere in the pages. All right, so we have a real movie database. We consider in this example just two tables. One table is called title. Another table is called cast info. Right, and of course, that person who creates mappings that map relational databases into RDF, that person should know the meaning of the tables, what each column and each magic number there means. Okay, so let's have a look. So in table title, we have what? Movie ID on the left, yeah, movie ID here. These are just some numbers. Here we have title in English. Here we have year, probably it's the year of production. And here we have kind. Yeah, this is a magic number. Yeah, so in this particular example, we have number 1 and number 2. And somewhere it should be written, and we can guess that number 1 probably refers to a proper movie like Django Unchained, and 2 refers to a series, like the Game of Thrones. Okay, fine. Now let's have a look at the table cast info. In the table cast info, we have what? Person ID, movie ID, in person role. So probably it says that the person with that ID, say N37, played some role in the movie whose ID is 728, that is Django Unchained, and the person's role is 1. And it should be written somewhere. That 1 probably means, actually I don't remember, probably means a male actor. And probably 2 means female actor, or the other way around. So 1 refers to men, 2 to women who played in the corresponding movies. Okay. So now we understand this little example in detail. And suppose now that the task is like this. I don't want to deal with the tables. I want to offer the users of the IMDb system an opportunity to formulate queries in Sparkle using, natural language or nearly natural language words. For example, movie, and has female actor. Or something else, this kind of thing. So, of course, I want to, because it's RDF, there should be a proper prefix indicating the namespace. So MO probably it's for movie ontology. And here, and movie is a class. And here, MO has female actor, it's a property, it's a binary relation. All right, so what is the task then? And the task then is to kind of populate this class movie, right, with movies, with IDs of movies. So I want to have something like this. It's written here. This is what it means to populate, to create RDF triples, saying that this URI refers to a movie. This URI is of type movie, and this URI is of type movie, and so on and so forth. Where I can get these triples, I can construct these triples myself using the information from the relational data. How can I do it? Okay, by querying the relational data. And this is the language. I explained the language using examples, and probably it should be enough for our exercises. So R2 RML mappings can be regarded as pairs of the following form. Here we have a triple template. It should specify what kind of RDF triples we are going to construct. And here there is an SQL query. And that query will get the data, the required data from the tables. Okay. Now, suppose that what I want to do is to populate the class movie. Yeah, I want to extract from the data all movies. Then what shall I do? Oops, just a second. I do the following. So the left-hand side, target. This is what the triples I want to obtain. Yeah, you see that this target triple template, it looks very similar to what I want to obtain. Apart from one thing, here in this curly brackets, I have a kind of a placeholder. And this is exactly what I want to retrieve, movie ID, from the database. IMDb : title / it will be part of the URI. Yeah, and here there will be a concrete ID. Yeah, for example, look in the first triple. It said that IMDb : title / 728. Yeah, 728 is here. Right, so this will refer to the movie ID. All right, so how can I select those movies? Yeah, and I select this movie by querying the source, by writing an SQL query to the source. Those who don't know SQL, well, just look at these examples and they will show you everything you need to know to answer the questions in the test. If you make errors, it doesn't matter. What matters is the idea that you understand, the basic idea. Okay, so what do we have to do here? I want, in English, so what do I want to do? I want to take this table title, and I want to select from this table all movie IDs. Okay, not all movie IDs. Those IDs for which kind is one. That is this one and this one. Right, and this is exactly what the SQL query here is doing. Yeah, I say that. Select movie ID. Right, so I indicate the column. Yeah, this is what I'm going to select. From title. Title is the name of the table. And then a condition where kind is one. Okay, so this pair will be a mapping. Yeah, and it's what it does. It shows how to map the relational database, the table title to triples like this. Yeah, so if I say apply this mapping to the database, then the result will be a set of triples like this. Yeah, converting relational data into RDF. Okay, so for one more example. So now, yeah, suppose we again have the same database with the title. Yeah, and here, I write magic numbers. 1 is a movie, 2 is a series, 1 is a male actor in table casting 4, and 2 is female. Okay, now what I want to do. Now I want to do, I don't want, in this example, I don't want just movies. for some reason, I want to use the terminology, the terms from the language, the ontology language given by Iago. Google if you want to see what Iago suggests. Yeah, and in Iago, yes, they have a creative work, and creative work, it contains everything: movies, series, documentaries, cartoons, you name it. Yeah, so all of these things are creative work. So here then we do what? Oh, then we don't need to discriminate between movies and series. Yeah, we want to select all movie ID from the table title. Yeah, select movie ID from title. Then all these guys will be selected as the values of movie ID here. Yeah, and if we apply the mapping to the tables, then we'll get triples like this. All these guys will be, all these triples will define, will populate Iago creative work with concrete URIs referring to movies, serials, and so on. Okay, one more example. Now I want to select, I want to select triples like this. Let's look here. That's a movie ID. Then I have a property has female actor. And then I have here an ID of a person, of an actor. So here it is N38. It refers to this one. Yeah, and why do we know that it's a female? Because here we have two. Okay, so what do we want to select? Right, now we probably should operate with cast info, with this table, right? And we want to populate triples like this here. Yeah, so what, but now I need two arguments. One is movie ID, another is person ID, right? And my triples should be of this form. Yeah, movie ID, okay, with a proper prefix. So IMDb title, movie ID. So this is a placeholder for movie IDs. Now this will be the property. This movie has female actor, IMDb person, and here is another placeholder for the corresponding person ID. Yeah, and what is the condition? How to extract this data? And then here comes the SQL query, which says what? Select movie ID and person ID from table cast info. Yeah, so I need this and this. Yeah, and I need pairs like this, such that, or for those rows where person rule is 2, equals 2. Okay, then we have, we'll extract movie ID, triples, movie ID, female actor, person ID, all these things which are given in the database. Okay, in the left-hand side, in these triple patterns, we can write as many triples as we want. They are indicating placeholders. Yeah, for example, what do we want here? Yeah, let's try and read what is here. So what I want to have is movie ID, production year, and here year, that will be a placeholder. And here is some indication that this number should be, sorry, this data should be treated as an integer number. Okay, and I have another triple, title, yeah, MO title, title. Yeah, so I want to extract three things: this, year, and title, and they should be organized in triples like it is written here. Yeah, and then it's very easy. It's simply, yeah, it's simply select movie ID, year, and title from the table title. And if we apply this mapping, we will obtain triples like this. 7 to 8, production year 2012, title Django Unchained. Yeah, just let me reiterate what is the difference between this data set and the this data set. Without knowing that say the table title has 4 columns. The first one is this, the second is this, year, kind, and probably some other information, the information about magic numbers. And the table can be extremely large, 75 columns, not a problem. Yeah, so you really have to be an expert in databases in order to query these databases. Instead, by extracting triples, what we offer the user, where is this? Wait. We offer the user RDF triples, where all the terms, first you can query easily and figure out that there is a class movie, that there is production year, that there is title. Yeah? And all these things are in natural language, and the structure of triples is easily understood, for example, by querying. So you don't have to be an expert in databases at all. And in fact, you can use a visual query language with terms like production year, title, male, female role, and so on. Okay, I'll give you one more example of a more complex mapping. Now, as far as I remember, in this complex SQL query, we need a join of 2 tables. Let's try and read what we have here. So I want to extract from the tables the following information. Person ID is a male actor in movie Okay, so what I wanted to show in this example is how to take a join of these 2 tables, nothing else. Now let's see. So I want to have a person ID is a male actor in the movie, and here I have probably it should be title here, not movie ID. Oh no, indeed it's a movie. Yeah, it must be a movie. No, everything is correct. So what I want to have are male actor in a movie like this. Yeah, it's a movie, not a serial or anything else. Right, and in order to extract this information, I need both tables. So what do I have to do? I want to have here movie ID in the condition that here the kind is 1. And I want to take the corresponding movie ID here and extract this person ID, provided that the person role is one here. Okay, so then the SQL query will be like this. So in blue, select title movie ID, that is, select from the table title, yeah? And select cast info person ID, that is from the table cast info, from the second table. All right, and where what? Title movie ID, that is movie ID from the table title, coincides with the cast info movie ID in the table cast info. And then additional conditions. And the person role is one. It's in the table cast info. And another one in the table title kind is one as well. So it's a logical expression which takes a join of two tables, and we're joining by this number, right? And extract this number and this number, provided that kind here is one and person role here is also one. Okay, so in your test, I'll give you something probably even simpler than this, and I'll ask you to write mappings similar to what we had here. Okay, let me then mention the following, that the idea of ontology-based data access is like this. The data, the real data, can be given in very complex tables from companies, banks, or whatever. However, the user is not supposed to be an expert in databases. A user is supposed to be just a plain person like you or me, who only knows the usual words, the usual terms for what the user wants to extract. Okay, and then this user can formulate queries in Sparkle using this terminology, standard terminology, maybe in Visual Sparkle, provided that somebody in the IT department have already written mappings that connect the relational data with the RDF data. Okay, now how it works? There are ontology-based data access systems, and they can work in two regimes. One regime is just physically apply the mappings and construct RDF triples. That is, you had a representation, a table representation of your data, and we apply the mappings and obtain just a lot of triples. And then the user Sparkle queries will be applied to these triples. Another one is it's called rewriting. It's a different technology, and this is what OBDA systems do. They do not materialize the RDF triples. You formulate your Sparkle query in the ontology language, and the system rewrites your query using the mappings into a proper SQL query over the data and executes it, optimizes and executes. Of course, this process is quite complex, but well, this is how it goes. Further, I give some examples of rewritings, but say here is ontology, Sparkle query, mappings, yeah, and this will be a rewriting, a proper SQL query constructed by the system itself automatically, and the system will run this query over the relational data. Okay, now let me finish this bit using one example here. Now, why this approach, apart from transforming tables into simple RDF triples, why this approach is interesting and where else it can be applied? Okay, so this is a typical example. Yeah, suppose that we want to query the web, or we want to write some software that queries the data on the web, you know, all possible data. And what I want to find, for example, in my example, I want to find all companies that produce and have produced telephones. Right, then I, because I'm not an expert, I just write a simple Sparkle query. Yeah? Find, yeah, reselect question mark C, so select this C, probably for company, and then such, well, I had a look at vocabularies that are available on the web. So C is of type organization, C made P, question mark P, made something, I call P, such that this P is of type telephone. Yeah, I had a look at the languages provided by some ontologies, DBO, FOAF, and Yago. Yeah, they provide this vocabulary, and I just formulate this query. Okay, so give me all organizations that made something, and this something is of type telephone. Right, so give me all organizations that have produced telephones. Yeah, no problem. And then you are satisfied. Such a simple query, you just run against RDF data on the web, and what happens? Nothing happens. And nothing happens probably because actually companies represented data in a different format. Yeah, for example, it could be that Siemens represented their information like this. Yeah, what's written here. So this is probably a model. Yeah, then DBO manufacturer, not made. Yeah, Siemens, and Siemens C22 is Yago Siemens mobile phone. Right, and similarly, you know, IBM Simon, manufacturer IBM, and it is of type IBM mobile phone. Right, what shall I do now? And what if there are other types of data? Now, ontology-based data access offers the following solution. We design an ontology that relates those classes and properties from the data to the classes and properties in your Sparkle query. Yeah, for example, I write the following thing here. Let's have a look. This one. It says the following. Manufacturer is a sub-property of maker. Meaning what? Okay, let me draw a picture. Meaning the following, that if I have here, I have manufacturer, then the system will deduce maker. So if something is connected to something by a manufacturer error, then there is also a maker error. Good, that's one. Number two, if we have a maker error, the maker error is right, we need to use something. Yeah, it's called inverse of made, which means the following, that whenever we have maker from left to right, then we have made inverse. Yeah, if this and this are related by maker, then the end and the beginning are related by made. Yeah, like how it should be in language. Fine. Then we say that the manufacturer, if we have an arrow which is manufacturer, then the range, the end must be an organization. Yeah, then this one will be organization. Yeah, the ontology, we define it like this. Yeah, whenever we have a manufacturer arrow, then the end will be organization. Right, then this one says that Siemens mobile phones subclass of telephone. Aha, every Siemens mobile phone is a telephone. And similarly, every IBM mobile phone is a subclass of is a telephone as well. We know these things from RDFS. Yeah, the only new thing here is inverse of, which comes from the web ontology language OWL, and I'll show you this language today. All right, now let's have a look at this data. So what do we have? We have Siemens C20. So we have here C25. Then we have manufacturer. And here we have Siemens. Siemens. All right. Now the ontology actually says that Siemens is organization and C25 is made by Siemens. Right. And then what can we do? And also we can, because the, right, here it's written, C25 is Siemens mobile phone. Yeah, so mobile phone. And then here it's written that every Siemens mobile phone is a telephone. So here it must be telephone. Yeah, and now everything is there. Yeah, so now I can answer the SPARQL query, right? Because C25 exactly satisfies the conditions here. Yeah, because is of type, oh no, sorry, not C25, this one, Siemens. Sorry, so it's not this, it's this. Siemens is of type organization, as required here. P is made by Siemens because of the green arrow, and this C25 is of type telephone. Yeah, so the SPARQL endpoint will return you Siemens and IBM. Now, although directly it doesn't follow from this data that these are the answers. So in order to answer this question, we need an ontology like this, some knowledge which people possess, but the machine doesn't know. Okay, so the last topic, and I'm going to explain it by examples, is some elements of building an ontology. Right, so I'll be showing you how to represent knowledge in two ways. One way is using the ontology editing and reasoning tool called Protégé. You can download it for free or is, you see, is a keyword. It's like disjunction, or woman add here. Now, what does it mean? This means that if I know that I have a person, then this person belongs to this class. It's either a man or a woman. Let me return to new share. Let me return back to this one. So I am at this point now. Every person can be a man or a woman. Meaning what? So I have a class person. Yeah, this is person. And this sentence, as I understand it, is a subset of man, woman. Nothing else. Are men and women disjoint? Can they be the same? Say here on this picture, I have an empty intersection. Is it the case that every man is a person? Is it the case that every woman is a person? Yeah, from this statement, it doesn't follow. Yeah, but maybe we want to add, maybe we want to say that every person, I don't know how it's in English, is a disjoint union of men and women. How about this? Every person is a disjoint union of men and women. Okay, let me first write this sentence as I represented it. I write person, and then I write subset of man, and then or disjunction. Yeah, how we write this in say disjunction or union. Yeah, better. Let's write union. Woman. Oops. All right, it's easy. The class person, the said person, is covered by the union of man and woman. Every person can be a man or a woman. If I want to say that men and women are disjoint, I have to write man intersection woman equals empty. In description logic, instead of empty, they write bottom or nothing. And if I want to say that actually every person is exactly the union of men and women, then instead of this subset of, I use equivalence. Okay. Then let's see, every mafioso is a person. Let's go back to the Protege editor. And now, if I want to say that every person actually is equivalent to a man or woman, yeah, I added here. I write man or woman. Now it will be equivalent. It is a stronger statement. Yeah, let me, for example, say something. Say, let me go to individuals and say that Vito is a man. Vito type, I add here type, class hierarchy, I add man. Okay, so I know that Vito is a man. And now I want to start the reasoner. How to start the reasoner? Go to reasoner. Yeah, and from, no, I know that Vito is a man and mafioso, and what else do I know? I thought that the reasoner should show that that Vito or Don Corleone is a person. How to see this? Annotation, data types. Okay, let me write a query here. Person, execute. Okay, so you see that Vito and Don Corleone are both persons. Although explicitly in the information, it's written only that Vito is a man. Yeah, so the reasoner can reason. Yeah, it can deduce that Vito is actually a person as well. All right, now let me move on and to show you some examples with properties. Let's try and represent the following fact. Vito is a husband of Carmela. Right, so we have two individuals, Vito, Carmela, and we need a property, a relation between them. So then we go to object properties, and here there is this top property, the all pairs. Now we introduce what I wanted, husband of. Husband of. Now, what can we do here? We can write, okay, we'll consider this later. Interesting domain. What is the domain? If somebody is husband of somebody else, yeah? So what is the domain? The domain normally is a man. So I can add here man. And the range, you see, probably it's a woman. Okay, fine. And now how to write that, how to connect these individuals by how to connect, I don't know actually how to connect Vito, individuals, Vito, property assertion. You see Vito, object property assertion, enter object property name, husband of, enter individual name, what it's Carmela. Okay, add. Right, so now we know that this information is explicitly added that Vito is a husband of Carmela. All right, let me return. Go to classes. I want to introduce a class father. Father. Okay, so what is a father? Actually, a father is a complex notion that can be defined as a man and with a child. Right. Then what I need, a property has child. I have man, but what I need is a object property has child. Oh yeah, I introduce has child. And then I write here father equivalent to no, I write like this, man, and then I want to say that the man has a child. Then I write has child, some, and then some what? Some person, for example. Oops. No, where is it? Oop. Oh, no, you see what happened? This father was automatically classified by the reasoner as a subset. It's below man, you see here. So it's a subset of man. And here it's a definition equivalent to man and has child, some person. Okay, new share. Let me show how to write this. So in the language of description logic, I write it like this. Father equivalent to man and intersection, and then I write exists, has child dot person. Right, so in the protege, I wrote man and has child, some person. Yeah, this is more natural language like. Yeah, in mathematics, in description logic, it's written like that. Okay, let's see further what I want to do next. I want to write that Carmela is a wife of Vito. How to write this? So what do I want to represent? Yeah, I want to represent the following, that here I have Carmela, here I have Vito, and what I need a property, yeah, wife of. To do this, in protege, I have to introduce this object property. Why it is object? Because it's between objects, this and that, and there are other objects related by this property. Yeah, and say, as I showed you, that Carmela is related to Vito by wife of. By the way, what do we know? Earlier I wrote that Vito is actually husband of. We'll have this kind of things. And actually, you see that these two properties are inverses of each other. Right? If X is a husband of Y, then wife is, sorry, and then Y is a wife of X. Now, how we represent this in mathematics, we can write it like this. Say I can write, normally I would write it like this, Carmela, comma, Vito. This pair is an element of wife of. Right, that the pair Carmela Vito belongs is an element of this relation vibe of. In description logic, we write colon here. Okay, so let's see what else. Husbands are men. Right, so how do we write this? Every husband is a man. Yeah, then we simply write husband, subset of man. So most of this notation, apart from things like this, is pretty clear. It's like in set theory. So when I ask you to represent some knowledge in this language, then, I mean, of course, I allow you to use any set theoretic notation. And oh, right, there is a question. Why do we represent a person class as a subclass of men and women? Would it be more reasonable to make it vice versa? Men and women classes are subclasses of a person. Listen, guys, I actually expected this question. It will be me, as your lecturer, who will be giving you tasks. And in this particular case, for whatever reason, the task was like this. Yeah, read here. Every person can be a man or a woman. How to understand, how to read it is another problem. Yeah, I say, if I take it literally, I say the following, that for every element of class person, this element is also an element of man or an element of a woman. And this is exactly what I represented. So if I ask you to represent certain knowledge, just do accordingly, don't invent. Of course, I agree with you that we can say that, right, man is a subset of person. Woman is a subset of person. From which what follows? Does it follow that every person is a man or woman? No, it doesn't. Still, you have to say that, that we need this, and still we have to say that men and women are disjoint. If you want to, you know, to have all the details. But when I ask you, represent this knowledge, just represent this sentence, and that's it. Yeah, it's not your business to represent all the knowledge in the world and what is natural, what is not. Yeah, I ask you to do some exercises. How about this one? A parent is a person who is a parent of someone. What's the problem here? The problem is that here it's a class. Yeah, class parent. Parent, by definition, is person, and a parent of someone. Then I would write like what exists, and here parent of is a property. Parent of someone, I can write here top. Yeah, this means the following, that if I have a situation, this element, sorry, this individual is person, and there is an arrow parent of, then this guy will be parent. Yeah, so this says there is an arrow of this with this name going here. Say, if you remember the notation of first order logic, I would write it like this. For all x, parent x, if and only if, or you may want to write like this, if and only if person X and exists Y, parent of XY. This is a first order representation of the same information. Okay, so now let's do the following. I stop here. If you want, you can download Protégé and play with Protégé and try and do the exercises I provided here. So next time I will show you how to model without Protégé, just in description logic, sentences like this, yeah, about a department. And that will be part of our preparations for the test. Then I'll return back and show you typical questions that you can expect in your test and remind you how to answer these questions. All right, and the test most probably will be, as I said, on the 9th of April. So that's it for today. If you have questions, then ask. If not, then we meet next week. That will be the last official seminar. By then, see you next week.